Okay, here's a video I did on that there bar graph circuit that you can find on my YouTube channel. Remember this?
Okay, there's a potentiometer around 5k ohms. Goes into the input over here. And there's the lights. And there's the circuitry. Come back here a little bit now. And then turn the potentiometer to the right. The lights will light up. Vary back and forth, and they go on in sequence and back off in sequence, like a bar graph.
Okay, so that was the video that I did on a bar graph, and I have the description here too. I have a description written here of how I did that. I can find that. I don't think I can do this on my. I might have to do this on my computer. I can't. I don't think I have description. I find description here. Let me see here. No, I can't do it on my iPad. I have to use it on my computer. But I had a description here of how to design this circuit, and you can find that on my YouTube channel. It's on the bar graph. It's called the Transistor Design Manual Bar Graph Demo. And if you click on the description, I give you all the steps of how I designed it. But that's just a description on the on this circuit. As far as actually design it and showing how it's done, I'm going to make a video of that now. This is the video I'm going to do. I'm going to make a video of me designing that circuit from scratch, and I'm going to show you how it's done, how I did it, how I come up with the design, every component, and everything. And that's what I'm going to show you next. Okay, what I'm going to do is I want to start out with the very basics. This is the actual circuit right here that we're going to build from scratch. Now, here's what I need to explain first of all, is that my transistor circuit design videos, they're geared towards those who are just learning electronics and would just like to learn how to play around with transistors and learn how to just design from scratch and just to have some sort of satisfaction of building a circuit that works satisfactorily. Again, I design only as a hobbyist. Okay, so this is my disclaimer. This is not a professional way of designing circuits. I do not design circuits for a living. I do not even design circuits for any kind of profit or anything. It's just for my own hobby only. So whatever I share here, I am sharing only as a hobbyist to all those out there who enjoy designing circuits on a hobby level. When it comes to designing on a professional level, do not use any techniques that I show here. Just take this as entertainment. Maybe learn what not to do sometimes. But if you're just in it just to enjoy the hobby for it, then you can probably just follow along and maybe even build the same circuits I'm showing you here to build. And that's kind of my goal in this here, is to show you how to design these circuits from scratch, to go through all the details of it so that you can do the very same thing and get the very same kind of results on your circuits. And then from there, you can take your circuits and you can upgrade them to however you like. You can add components, take away components, you can change component values, do whatever you want, but this gives you a basic working circuit for you to play around with and to experiment with. Okay, now with all that in mind, that was my disclaimer, so now on with the actual circuit. Okay, the first thing I like to do is I set myself up a voltage supply that I want to use. Let's say that I want to use a 9-volt battery. Well, usually around 7 to 8 volts is like nominal, so I'll design this with a 7-volt source, a VCC of 7 volts. Now, the first thing I need to look at is why did I design a circuit in this kind of fashion like this here? Alright. The whole idea is for the output to be a bar graph. This would be the first LED that would come on as the voltage input increases in value. As this comes on to a certain voltage value, as the voltage increases farther on the input, the second light would come on, and then the third one and the fourth one, and it would come on in a sequence as the input voltage rises in value. So in order to have that happen, I need to take the signal that comes from the first transistor input here and relay that signal, first of all, to an output, and then to relay that signal to another transistor so that that transistor can send its output out and continue on. So this is a chain reaction. This one here is a result of these three. This one's a result of these two, and this one resolve this one here. So each one is chain reaction here. Each one is sending the signal from one to the next, all the way down the chain of command, chain of line here. So that's the reason for the circuit being designed in this fashion, in this kind of a way. Now, here's how I'm getting the component values. First of all, I like to assume a beta minimum of 50. Okay. Now, assuming you have a little bit of an understanding of how transistors are turned on with base current and things like that, and emitter base voltage and things like that, just with the assumptions you have a basic understanding for transistors. Even if you don't, you can still build a circuit and have it work. But I assume a beta minimum of 50, and I look at the calculation or the data sheets and find out that an LED may have around 2 volts and around 30 milliamps of current flowing through it to light up nice and bright. So I'm going to use that for my values to solve for circuit resistance values here. Alright, now the first thing I'm going to do is I want to solve for the resistance R1 here. That's right here. Now, I'm also going to assume a voltage drop across from collector to emitter. I'm just going to choose a voltage drop. That's just the way I'd like to do it. I just choose something. So I'm just going to choose, I'll call this voltage, collector to emitter. I'm going to choose a voltage of, let's say, I'll just make it 1 volt. Just for, I don't know how it's going to work, but I'm just going to try 1 volt and see if it works at 1 volt. Alright. That means then that when this transistor is operating, it's going to have a 1 volt drop across it. Now if it had 0.2 volts across it, it would be in saturation. It would not be in the active region anymore, it would be in saturation. And saturation means that any increase in base current, the transistor is already saturated and it's got the full amount of current flowing through it, and therefore there is no more change in collector current with respect to change in base current. And I want to keep this in the active region and not in a saturation region. So again, with that in mind, instead of having 0.2 volts, I make that 1 volt drop across there, and that keeps it in the active region. Alright, now to solve for the resistance R1, we're going to use Ohm's law. If I have a 7 volt supply voltage here, and I have 1 volt dropped across the transistor, and we said 2 volts will be dropped across the LED, I will take the supply voltage, I will subtract the collector emitter voltage, and I will subtract the LED voltage, and that would give me the voltage drop across the resistor here. Because we go with a Kirchhoff's voltage law, it's called a voltage loop, and you start from one end and you go all the way around, back around the loop. And in that loop, we find that there is one value here that's not known, voltage value, and that would be R1. Now to solve for R1 value, we can get the voltage simply by, like I said, taking the supply voltage and subtracting these other 2 voltages here. So we have 2 volts here and 1 volt dropped here. That's 3 volts. That 3 volts subtracted from the 7 volt supply gives us 4 volts left over. Well, that leftover voltage has to be across the last component here, which is R1. So if R1 has 4 volts dropped across it, and we want 30 milliamps of current flowing through the LED, and the R1 is in series with the LED, so we now have a series going with electron current flow. We have a series current flowing through the LED R1 through the transistor back to the supply voltage. So therefore, since we have 30 milliamps flowing through here, again, according to Ohm's law, we take the voltage across R1, divide that by the current through R1, and that would give us the value of R1. So 4 volts divided by that 30 milliamps will equal. Okay, that will give me 133 ohms. Now I know that a nominal resistor value is 130 ohms according to the chart here. So 130 ohms would be R1. So we make R1 130 ohms. Okay. Now that will establish that whenever we have 1 volt dropped across a transistor and 2 volts dropped across here with 30 milliamps flowing through there, we would have a volt drop of 4 volts across R1 with 130 ohms, and that would give us our value. All right. Now that R1 is known as a current limiting resistor. R1 determines the amount of current that's going to flow through the LED, as we can see through Ohm's law again. So now we know that we have to turn the transistor on, okay? And if we were to assume a beta of 50, a minimum beta of 50, then we say then that the collector current, which would be the current flowing through the LED, again, now if you go down into real deep transistor circuit design, you find out that emitter current and collector currents are a little different. And there's the alpha, and then you have the beta and things like that. Beta, collector current divided by base current. Alpha, the collector current divided by emitter current. And I think that's what it is. And these things. And so there's a lot of variations involved here. But if we go by what I like to go by is just ballpark figures. When I do my designs, it's ballpark figures as much as I can. And so I'm just going to assume the collector current to be the amount that the emitter current is, and that's 30 milliamps flowing through here. All right, so with 30 milliamps flowing through as the collector current, if I divide that 30 milliamps divided by the 50, which is the beta minimum, that will give me the base current flowing out of here. So let me calculate that. Okay, so I took the 30 milliamps collector current, I divide that by 50, which is beta minimum, and that gives me around 600 microamps for the base current. Now, a rule of thumb is you want to make the divider current, which is going to produce the base voltage, okay, for the transistor. You want that divider voltage or the divider current flowing through there to be around 10 times greater than the base current flowing through here, which is 600 microamps. And the reason you want to do that is because the 600 microamps is flowing through here, that's also going to flow through RB2 back to the supply voltage, and that's going to cause a voltage drop across here, which is going to decrease the voltage at the base, which is called divider current. Is what it's going to do. It's going to load the current, the divider, and cause the base voltage to drop, and we don't want that. If we make the current flowing through the divider 10 times greater than that there, then this will have very little effect on the voltage being applied here. So if this is 600 microamps, we take that times 10, that will give us now 6 milliamps. Okay, so we now have 6 milliamps flowing. Now I'm going to go with the conventional current flow now from positive to the ground, and that's 6 milliamps now in the divider. Okay, so we got 6 milliamps flowing through here now. That will produce for us a great enough current through here that will allow this current that's flowing through here to not upset it and cause the voltage to be changed here at the base. Alright, now with 6 milliamps flowing through here, we can take that 6 milliamps and we can multiply that times this resistance RB1 to get us a voltage drop. But we don't know what this RB1 is, but we do know what the voltage drop is, and here's how we know that. If we go back to our output here, we have 4 volts dropped across this resistor here, plus an additional 2 across here. So from the ground to the emitter here is 2 plus the 4 is 6 volts. So we have 6 volts at the emitter. Excuse me. Now, for the transistor to be turned on, we have to have at least 0.7 volts at the base with respect to the emitter, and that would turn the transistor on. So now we have a base voltage of 6.7 volts. 6 volts to the emitter plus 0.7 gives us 6.7 volts at the base. 6.7 volts divided by 6 milliamps will give us the value for RB1. Okay, that gives us a value of 1116 ohms, but we go with the nominal value of 1.1K. Okay, now now that we have that 1.1K established here, we want to solve for RB2 now. Now RB2 would be the supply voltage minus the base voltage, and that would give us the voltage drop across RB2. So 7 minus 6.7 volts would be 0.3 volts across RB2. So we have 0.3 volts dropped across RB2 divided by the 6 milliamps plus 600 microamps of base current. And let's see what that value comes out to. Okay, that would give us 45 ohms. A nominal value would be 43 ohms or 47. I'm going to choose 47 ohms for that. Okay, now the thing to keep in mind is that in the description on the YouTube video that I did this on is a lot different than this here. It's the same techniques, but different value numbers and things, because I used a different value. I think I used 0.5 volts for the VCE instead of 1, things like that. So you're going to have different values on the resistor values. They're going to be completely different and things, but it's still the same design techniques, the same thing. So if this works this way here, doing a different way here now with different numbers, and then the design techniques are pretty well established to use almost any kind of values you want to use for VCE and beta minimum and things like that. But getting to the circuit here as it's built here now, the light is light up here now. I'm going to check the voltages here, and I want to first of all check the supply voltage. I check the supply voltage here, and I'm around 7 volts. So I'm looking for 7 volts for supply voltage. Now I want to check the voltage across the from ground to the emitter. I should have around 6 volts roughly. So I'm going to check that right now at the emitter here, right there, and around 5.89. That's very close to 6 volts, but we're within that range. I want to check the voltage drop between collector and emitter. We said we want around 1 volt. So let me check here now. This is hard to do with one hand. I might have to put this on the pedestal here. Hold on one second. Okay, so I'm going to check now across the collector to emitter. So here's the emitter hooked up here and the collector here. And I'm getting 1.04 volts. There's a collector emitter. 1.04 volts, and there's our 1 volt that we're looking for. So we are getting our values that we want here. We got our 1 volt across the transistor. We're getting our close to 6 volts here on our emitter voltage, and so we're within our voltage range that we're looking for. So we have that part established. We designed it according to our calculations and our voltage values. As we actually build it and checked it in an imperial way, it is actually coming out pretty close to our calculated values, and that's what counts. Okay, so now I'm going to show you how I start designing the next part of the circuitry, how I calculate those values now. Okay, now the next component to be calculated for would be RB right here of transistor Q2. We have R1 established, we have RB1, RB2, so we have all this circuitry, all of the resistor values established. We have the calculations of the voltages and the currents. And so now we can move on to the next component that's connected to that in the chain, and that would be RB here. So let's take a look at this. If we have 6 volts sitting right here at the emitter, let's assume, since we have 0.3 volts up here, let's arbitrarily choose 0.3 volts dropped across each one of these resistors now. So if we have 0.3 volts dropped across here, that would be 6 volts minus 0.3 volts would give us 5.7 volts right here at the base. If we subtract a base emitter voltage, which is nominal of 0.7 volts, usually to turn a transistor on you want to be between 0.6 and 0.8 volts, so we use 0.7 volts. That would drop this down at the emitter now to 5 volts. If we have 5 volts sitting at the emitter and we have 2 volts dropped across the LED, that leaves us with 3 volts dropped across R2. Okay, we had 4 volts up here, now we're down to 3 volts here. So now we have 3 volts dropped across R2. Again, we calculate using 30 milliamps for the LED current, so we take 3 volts divided by 30 milliamps, and that will give us the value for R2. And that value for R2 now comes out to 100 ohms. So now that gives us 100 ohms for R2. Now we want to solve for RB. Now here's where it's a little bit different. Up here we had a voltage divider to provide a voltage. Now that voltage was established by the voltage divider up here to provide the amount of current flowing through here, which we had to take 10 times the base current. So remember, we had the base current being at 600 microamps, and we wanted the current through the divider to be around 6 milliamps, which is 10 times that. But now as we come down on the next part of the circuitry here, we find out that we don't have a voltage divider. We are taking the direct current coming through the transistor base as our input current. So we now have to go with a little bit different value. We have 0.3 volts. We have 6 volts at the emitter here, 5.7 at the base with a 0.3 volt drop across the RB. We now take that divided by our 600 microamps because we have, again, we're using 30 milliamps collector current. Divide that by a beta minimum of 50, and that gives us our 600 microamps. So now we take 0.3 divided by 600 microamps to give us RB, which comes out to about 510 ohms nominal. We do the same thing down with the next two stages. We do the same exact thing. We use 510 ohms for the next two stages because we're going to take 0.3 volts across each resistor, and we're going to use 600 microamps as our base current, and that will give us our RB. So that's why RB is all the same down this whole chain. The only resistor that's going to change now is going to be R3 and R4, which are the current limiting resistors for the LEDs. That's the only resistors that we're going to be solving for now. Okay, so again, like I said, we want to keep RB the very same value because we still have the same 600 microamps flowing through each base resistor, and we want 0.3 volts dropped across each base resistor. That keeps everything nice and even. So as you can see, the output kept on dropping by 1 volt from 4 volts to 3 to 2 to 1 volt, which makes it pretty convenient also. The last two resistors end up being 33 ohms. This one here end up being 68 ohms for this one. So R3 is 68 ohms. This one R4 became 33 ohms. And then I built the circuit, and I have a potentiometer right here. And there's a circuit right there. And I was able to get one last LED in there, one last circuit in there that has no current limiting resistor whatsoever. And the reason why is because of the current that's going through there is maxing out now. There's no need for the resistor in there because the voltage applied to it is around less than 1 volt because we have 2 volts. By the time we get to the last transistor, we're going to be less than 2 volts anyhow across there. So there's no need for it there. So that's just driving, the transistor is driving the LED straight through. Okay, so as I turn the potentiometer, now you can see how the lights light up one at a time from left to right. I'm just turning nice and slowly here. And go back and forth. And so there it was, the steps of how to make this to work. You can see I'm turning very slowly here, back and forth. I can turn fast. Now what I'm going to do now... Okay, I had this set up here as a bar graph now for a radio sound. The only problem though is that I have to use a jack, a phone jack in here, and that's going to turn the sound off on the radio. But at least we can watch the lights going up and down. So I'll let you hear a little bit what's going on here on the radio. Now what I'm going to do is I'm going to plug in now. I'm going to plug this in now, and I'm going to turn the volume all the way up. And now there's the lights going up and down according to the sound on the radio. Okay, so that's how that can be used as a light organ for a radio. I'm going to turn this down a little bit here now. Okay, so we've seen how that works now, and there's the circuit, how it was designed, and I'll take in more detail later on here whenever I get this fixed more better. Now this was designed just with arbitrary numbers and stuff like that, and so that's why it takes a very heavy input to make the lights work and everything. But if I really wanted to make that work in normal volume and things, then I would have to just redesign it for specific voltages and everything to get it to work more a lower value of input and stuff. Right now you have to sound it pretty much almost all the way in order to get any kind of input to show up here, an output. But it's just a basic circuit to show how that can be made out of a transistor, basic circuit of how to make a light organ. I'll try to improve on it, like I said, and I get a better circuit built, then I will make a video of that too and show you how to design a much better circuit than this. But that's all for right now. Have fun in the shop. Bye.